subtopic, which is actually about the shortest path given a weighted graph. We learned about an unweighted one, and we count the number of edges, and here we have a weighted one, where the weights over the edges count. Now, given this graph, question is that, do I need to always calculate, like, for example, from A, I have to, some things I want to go to E, for example. Then you have to think about all possible paths. Say, for example, I can go AC and then E, this sum up to 5 as a cost. Then you have another way that you can go A, B, then C, then E, for example. This is 11, 13, for example. Yeah, you have to count everything, and it's given graph with hundreds of nodes and edges that they are weighted. Keep track, calculating to find the minimum one. It's actually a time consuming. Therefore, a scientist called Diachrous, and the algorithm is also named based on his name, in 70s found a way that you can develop a so-called greedy algorithm. Have you ever heard with this concept before, a greedy algorithm? What does it mean? Do you know what's greedy mean? Okay, you are in the end of the second year almost, and you want to start the third year. Okay, maybe in the object-oriented course, maybe you have heard about this concept, but just repetition. A greedy algorithm is an algorithm that updates the local status time by time. So, what's the optimal solution at this moment, for example? It's like you start as a blind. You don't need to look to everything. You're not totally blind. You can just see a short distance from where you stand. I'm at A, at this position. I want to start. I just can see my neighbors. I don't see them. Then just do the optimal thing here. You are looking for the shortest distance. Take the shortest one from A. Then once you're in B, for example, you can look further also. Then you update back things. And this is actually that you always look for the optimal case in the local position where you are, which will actually enhance the global optimality of your algorithm, whatever you are looking for. There are many kind of greedy algorithms. The greedy algorithms can be a search algorithm, can be actually a shortest path algorithm, can be whatever. But it's not necessary that you start from the optimal. You start, and then every time you update the optimal until you finish. Okay, with Diachrous also, you don't need an end point, because you will apply it first for the whole graph, given graph, and then what is the shortest distance to reach, for example, edge? It's already computed, because you will compute it once for all nodes. From the starting point, you just need only to define where you want to start, and then all is calculated, so you just can invoke the information. Okay, here's Diachrous algorithm. The idea that you need first to initiate a queue, and this queue is empty. And if you notice, we use a queue a lot in our algorithms, so it's actually a good data structure. So it's initially empty at the beginning, and we have here an array. You can call it a stack also as well. It's also empty. We have a for loop at the beginning here. For all vertices except the starting vertices. All vertices without the starting one, we do the distance to them like infinity. And this is the key here. Why? As I said before, I want to update this distance to reach this nodes or these vertices. So they initially like infinity, no value, I don't know, it's something. And then every time, maybe you look, can I reach this node with less than infinity. You say yes, for example, 10. Okay, update it to 10. Next time I see another way to reach the same node from another node. And then the cost total is 5. Is it less than 10? Yes. Then update. And that's the idea why we start all like infinity. And the starting one is 0 initially. This is where we put it. Now, we insert to the queue all vertices minus s, okay? Or I think with s, so at the beginning, because here the algorithm say it is v. Then, as long as the queue is not empty, we get the minimum as starting point. What is the minimum? Is the start. Why? Because all vertices has the distance infinity. And the only starting point is the vertices where we start is 0, right? So we get the first node. And what we do, we add it to what we define here as an array called S, or a set. So then initially it was 5, then it will take the starting point. Then from the starting point we can look to the adjacent. Okay. Get all adjacent, look to their time. The time for the adjacent, for example, let's say I'm in A, and here I have B, for example. This is actually the distance for it was initially 5, and this is 0, and here we have a weight 2. Getting B, you ask now whether the distance to B is less than the distance to A plus 10. The distance to A plus 10 is actually 10. And what's the distance to B? Is infinity. Is it less than? No. Then update it to B. So this one will become actually 10. Good. Then we actually do this for all adjacents. Assume that now we have also C here. And with C, I can go, for example, with 2 to C. Initially empty. Can I go to here with the list cost? Yes. The cost to the A plus 2 is 2, less than infinity, then I can go to C. Good. Do we have more adjacent for A? No. And both B and C will be queued. Now, can I go? Let's assume that the next that I discovered any queue is actually the queue is C. And we have here, for example, 3. Can go from C to B with B. Good. Now, what's the adjacent for C? B. What's the cost to reach B? 10. The initial one. They updated from A. Okay. Now, C has a cost 2 plus this edge 5. Is 5 less than 10? Yes. Then you update this 10 and you say 5. And this is why we call it a greedy algorithm. So initially, it was B was actually infinity. Then I say from A. I'm just, someone who's actually can see, long distance. I can just see the next step. From A, I can see just only these 2 edges. This is why I initially say I can reach B from A with 10. But later on, I see, okay, I can also do from C. Then I can go, the shortest path is to go A, C, B, and not to go A, B, for example. This is the whole idea of the algorithm. This is why it's greedy. Now, let's apply it to this example. It's a bit repetitive, but just only we will go quickly with it. If you did not understand something, just raise a hand. This is actually the queue. We inserted all nodes, A, B, C, D, E, all of them initially infinity, and the starting is 0. Let's start with A. This is the minimum. We dequeue it, look to its neighbor. What neighbors it has? It has B and C. Then we update the distance, because both of them is infinity, and 10 and 3 is less than the infinities. So then
B will has distance 10, C will has distance 3, and this is the stack remain. Next, I will get the minimum from the Q. What is the minimum? Is C. Okay, we start from C, get it out. What is the neighbors for C, or the adjacent? Okay, from C, I can go to B, I can go to D, and I can go to E. These are all adjacent. Okay, then I need to update their distance. So from C to B, I can go with 4, and it's initially 3, then 7. Then I will update B to 7. Okay, and also D and E. This will be 8 because it's initially infinity. 8 is less than infinity, and 2 is less than infinity. So this is will be 7, 11, 5. Get the next minimum. The next minimum is 5. So it is E. We get it out, and we look to its neighbors. It has D as a neighbor. Okay, good. D, the distance from A is 11. Now, if I say, okay, from E I can go to D with 9. E is reachable from A with 5. Then 9 plus 5 is actually 14. It's greater than 11. Therefore, I will not update D. Okay? So, then the next is actually 7 with which is B, where I can go with 7 to D. 7 plus 2 is 9, less than 11. Then you will update D to 9. Okay, so this is the next minimum, and then you update this one here to 9. And then, do we have something remaining? Yes, we can go from D to actually to E with 7, but it will be actually more close to E, because it will be actually like 16, and E is reachable from A with 5. Therefore, you just finish the algorithm. Now the question, okay, I updated the cost. Then the algorithm does not mention, but this is a simple thing that you can add. It just shows you how to calculate and update the distance from A. You need to keep an information about the predecessor, because later on you need. Now what I know is that D is reachable with a cost called 9 from A, but what are the edges? So then you need the same way that we did in the unweighted graph. If D know about the predecessor of it, then you just stack them. So for example, you can say D is reachable from, I don't know, from B, and B is reachable from C, I think, and then A. And then you bring them in order A, C, E, and D, and this is actually the path from A to B. But then you need just only a simple line here somewhere in the algorithm. Where is the algorithm here? To store an information inside the node about its predecessor. Okay, good. Understood. If yes, then we can continue with a totally different from the shortest path here. It's called the minimum spanning. Okay. Different from the shortest path, the minimum spanning tree, if you need to think about it, how I can visit all nodes, okay, from anywhere, meaning that the graph is connected. You remember the type of graphs? We have the complete graph where each pair has an edge between them, but the connected graph is actually where we have actually a path from any two nodes, and we explain the difference between them. Just only to remember, we have A, B, and C. Now, the graph is connected if we have an edge between any two pairs, so we can say this one, this is a connected and complete. Okay? But here we need a connected graph, meaning that I need a path between any two nodes. Is there is a path between B and C? Yes. Is there is a path between A and B? Yes. Is there is a path between A and C? Yes, I can go A, B, C. Okay. For example, if it's like directed is this one, then there is a path here, but there is no path from C to B. If it's a directed. Now, just let's assume it is not a directed graph. Okay. Because it depends whether we have a directed or undirected graph with the way that we go. Okay, now the question is that sometimes I need a path that allows you to visit all nodes, so meaning that all nodes are connected with the minimum cost over all the graph. Let's take an example. This is ABC. Let's assume that we also have this here. Okay, and I want to have cost here like 2, 1, and 1. Let's assume that ABC are actually cities, for example, or I don't know. And each edge between them is a road, following this example here, or the slide. And this is our area, and you want now to have or build the real street. So this street exists on the map somewhere, and now you actually want to create them in the real life. Okay, so where cars can cross them and people can go through them. But you have like budget, and you want to spend the budget so such as A, B, C are connected. I can go through them, but I need the minimum cost to create the roads. Theoretically, it's possible to create a road from A to C, but it will cost you 2 million, for example. Also, I can create from A to B and B to C. Each one of them is 1 million. Okay, it's good. Now, which I want to select. Ideally, if I select this one, A to C, okay, to have this road and create it, if I selected this one, A and B, C become connected, still I need B connected with them. Then maybe I can choose this one or this one, they become connected, but the cost will be like 3 million, right? To build the roads. So I will create this one, and I say, okay, I don't need this one. It exists on the map, like let's say it's dotted, but it's not really existing. Now the cost is 3 million. Can I go better? Can I say yes? Okay, let's go with this one. Move this one. Then I can select actually to go here, where the cost is actually 1 million, so 2 million total to keep the cities connected, and I save money. That's the idea. What's the difference between shortest path and the spanning tree? And by the way, there is a reason for calling it spanning tree, because at the end we will not have a graph, we will have the format of a tree. We will explain it later. But what's the difference between shortest path and the spanning tree? Given this example, if you look here, if I just want to follow Dykera's algorithm, what it will do, let's say this is one key here. Let's start initially. I am starting at A. I will just follow the algorithm that we just explained, Dykera's algorithm, or for the shortest path. This is initially infinity, right? Then you say, okay, from A I can C, I can go to B. Then this is 0. 1 plus 0 is 1, this is infinity. This will be updated to 1. From 0, from A I can go to C with cost 2. Then this will be updated, this will be 2. I'm now looking for the shortest path, not the spanning tree. Okay. Now let's go with B. We finished from A, start. Let's start with B. B has an adjacent C, right? With the cost 1. 1 plus 1 is 2. But C is already 2. So it's not less than 2, it's 2. Okay, they are equal. Therefore, I will not update anything. So then the included edges for me is this one and this one. Its minimum, the shortest path, looking always to the minimum from the starting point. But for the spanning tree, It's look to the sum of all edges that in total makes all nodes reachable from each other, but at the same time is minimum. Now, this is here, the minimum cost from A to C. Okay? If I go this one and this one, it's 2, 2, but I will not take it. The algorithm will tell you if they are equal, just forget about it in terms of short distance to travel. But in terms of spanning tree overall, as a spanning tree where all nodes are connected, it is not a spanning tree. So this is selected with diacritics, and this is selected with diacritics. But if you count them or take the weight of them, it will become 3, not 2. With diacritics, with the spanning tree, I will select BC and not AC. This is just a simple difference between them. Can I have with the shortest path the diacritics algorithm a spanning tree, a minimum spanning tree? Yes, maybe some special cases. Depends on the given algorithm. Most of the cases, no. Then the spanning tree is something totally different about the diacritics algorithm. And we will see that they somehow have the same way of a greedy algorithm, finding the next edge that I want to consider in the spanning tree, but the result at the end they are different. Okay. So this is here just only formalism that we need a tree that connect all vertices where the sum of the weights is minimized. This is an example. Here is a graph with some edges, and the blue one, the colored edges, is actually the selected one for the minimum span tree. If we actually sum the overall weight for them, it's become actually 37. The question, can we have more than one minimum span tree for the same graph? Yes. So here, for example, if I update BC and selected AH, for example, instead of BC, all nodes will become the graph, the result of the graph is connected, but it's the same weight at the end, it's also 37. Therefore, we have a different minimum spanning tree, but as long as we are in. Good. These are some properties of the minimum spanning tree. We, at the end, the number of edges is the number of vertices minus 1. And you can actually apply it here. So, for example, how many vertices we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 vertices. Then I expect in the minimum spanning tree I will have 8 edges. Let's look to the colored blue one. 1, 2, 3, 4, 5, 6, 7, 8. So this is actually in terms of number of edges. The minimum spanning tree has no cycle. You don't have a cycle in the minimum spanning tree. And I have explained this in this graph here. You will select this road and this road, but you will not actually take this one. Because they are connected. You don't need more extra cost. If you have this cost, it will be an extra, it will not be minimum. The idea is to have the nodes connected with the minimum cost. Yeah, it might not be unique, and we have explained this in the previous exam. Now, how we can actually build the spanning tree? How we can do that? Oh, it's the same slide, right? Okay. Slide's not better. Okay, I see the color now. Okay, so here is the simple algorithm. The idea is that you need to create a set of edges that you need for the minimum spanning tree. Identify what are the edges that I want to include in my minimum spanning tree. To do that, you create a set, and this set initially empty. And then you add edges to the set. The set is actually a subset of the minimum spanning tree. So it's part of it, because you update it each time until you actually have the real minimum spanning tree or the actual minimum spanning tree. As long as you add edges to that set, you need to add a safe edge. A safe edge that respects the minimum spanning. And what is the safe edge for us? This is the question. Let's look to this graph. This is a graph, and as you see here, the question, let's assume that initially the set is 5. We don't know the minimum spanning tree yet, and we want to add edges. We ask the question, is CF as an edge safe to be added or not? Should I consider it or not? How I should think about it? Okay, then we need to use this. I will not draw the whole graph, but I will just draw part of it. You have CFE and A. F, E, and we have A also as well. I don't know, I use the capital letter. Yeah. And yeah, these are the edges between them. From C at least, and we have B also. Let's just have it. I just draw the part with C, okay? I don't want to go further. I know we can go from E to somewhere else. Just this is what I want to explain next. We have A. A is where we want to store a list. So this is as a list. So I will call it the minimum spanning tree. Okay. This is the list of edges that I want to add. And initially it's 5. It's empty. We have nothing. Want from you to think about the edges that I want to add is a connection between a node and the other node. So you need to think as follows. You need to create a cut. I will start from C. This is my cut. Now it's like an island, has C and all other nodes in somewhere else. Now to connect this island with this somewhere else, the question is, what is the minimum thing? If you look from C, I can connect it with the word around it. 1, we have 3, we have 9, and we have 12. And it's clearly to connect C with the word outside is to take the minimum. Then I would say, okay, this one is safe. This is the first explanation for what is called a safe edge. It will become more clear in the next slide. But you can think about it like this. Now once it's added, my country will not become just one small island. It will consist of 2 islands. Therefore, this is my word now. C and F is part of the minimum spanning tree. And now I want to discover from C and F how I can go to the outside, from which road I can go. And always you choose the minimum. Okay. Then here the question is, what is a safe edge? And here are some definitions for you. What we have here is actually the minimum spanning tree that I just created, but it's not complete. It's a subset of the real or the finished or the largest minimum spanning tree, but still we have to continue. Okay, and now these are the edges that connect me with the other word. We have still A, B, D, E are not connected. Therefore, I will split B minus S and S. So these are the 2 words. B minus S is A, is my minimum spanning tree. It's a subset of the minimum spanning tree. And the other nodes in S is actually not connected yet. And we want to discover which one to add. I have to create a cut. I mean, this is if you just have it in the middle and you try it like that. But in algorithmically thinking, technically, the idea will be different. It's like a cut, but not a real draw cut. So here is a cut. This is theory, okay? here is the cut. Now, if you look to the cut, it says that the cut respects the minimum spanning tree. Why? Because it does not cross any edge in the minimum spanning tree. This is my minimum spanning tree in the blue color. Is this cut that I created cross any one of them? No. It does not cross any blue color. Okay, but we have edges here. It's not part of the minimum spanning tree like this one from I to H and from I to G. Can I draw the cut in a way that I can't actually cross the blue one? No. So think about it. I can go, for example, this way, and then I want to go in. How I can go out? So you have to cross. Then this will not be your correct cut. You have to create a cut in a way that you don't actually cross the edges in the minimum spanning tree that you create. Here, for example, when I created the cut first, okay, the minimum spanning tree was initially empty, has nothing. Therefore, I just choose this one. Now next, I choose this one and this one. This is my cut. C and F has, the minimum spanning tree has just only one edge, this one, and this cut does not cross it. Good. Now, what does it cross then? It crosses other edges. This edge is called light edges. It's not safe yet. It's called the light edge. The light edge is actually what is connected our minimum spanning tree with the word outside. So look to them. C and D is a light edge because it connects the minimum spanning tree with D. F and E is another light edge. A and H is another light edge. So it's an edge that the cut across them, and these all of them is called light edges. But the light edge that I'm interested in is the minimum. Okay, which one now to choose to expand our minimum spanning tree? Then you look here and you select CD 7. 7 is the minimum. And it's the unique light edge in this case. Okay. So you can call them all light edges and you can choose the minimum, but in terms of definition here, the light edge is the minimum. Then we have just only one light edge here. This actually CD, which I will select next. Once it's selected, and you want to expand more, you have to draw a new cut. Okay? Because now this cut crosses CD, and you have to create it in a way that you don't actually cross the edge. So then next time I will draw it like this, E, and go here and go after that, and then you come down to avoid crossing this edge. Then you think about the next safe edge to add. This is just only the theorem that we have, and it's again a greedy choice probability, because every time you need to add a minimum, you need to update the things. We need to start where we have nothing and then look what is the next and update. In terms of algorithms, we have two algorithms to do that. One is called Kruskal's algorithm, and then we have prime algorithm. They're somehow technically similar, but just only slightly different in the way that how they build. With the Kruskal, they start with building a forest and connect that forest, meaning that they build a tree here and here and here and here, and they approach a way to connect all these, the forest into one tree. So the output at the end will be one minimum span. But they will build it from different locations and then connect all of them together. With the primes, no. With the primes, we start building the tree from one node and expanding from that node. Okay? That's the main difference between them. Both of them are greedy algorithms, and here is Kruskal algorithm. How it works, we need the minimum spanning tree is initially empty, the list of edges that we have. Then you go to all vertices in the graph that you have. You make each vertices as a stand-alone set. Okay, how to think about it? They are islands. Each of them currently is separated, and you want to form a country later on. Okay, one big country from these islands. Okay. You want to start connecting them, but the connection will not start that we connect all like together. No. Okay, we want to form a country and let's go and just invite people. It will not work like this, but they will make some friendly relationship. The island A and B now they are close to each other. They will format just one part of the country, and then C and D somewhere else. They are in the north, for example, and they are also in a closer relationship. They decided to have like a small consortium there. So we have now two consortiums. Then they invite actually each other because there is a relationship that maybe connect them later. Therefore, we build it from several locations. This is why we said we will start building a forest, not a tree. Therefore, initially, each node is actually a set, standalone set. Next, what we want to do, we of course need to create the list of edges that we want to visit. Sort the list of edges in an increasing order, from the minimum to the maximum, depends on their weights. Then for each edge that we have in that list, what we want to do, the edge actually has a start and end. So we have an edge, for example, UV. This is an edge. Once you get this edge, initially U is a node and B is a node. Both of them is sets, and they are disconnected. If they are still the set of U and B, they are not equal. Take the union of them. Then, if they are not equal, make a union. Then U and B is not anymore disconnected set. They are one set. Okay, so this one will become one set. Okay, how it works? Let's look here. Let's start from A there. Sorry, I mean the figure on the left here. I will take this just an initial because Kruskal algorithm we can start from the minimum, right? You have the minimum. Then you need to order the edges in ascending order. This is the minimum here is with 1. Let's go with this one. The edge is actually say H and G. This is the edge. H is a standalone set. G is a standalone set, and every other node here is a standalone set. Is the set of G and H are equal? No, they are not equal. Take the union. This means that this H will be taken. Now H and G is in one set. Let's continue. The next step, I will take the minimum. H is 2 between C and I. C and I, they are still disconnected H sets. Therefore, take the union. We will take them. Next, I will choose the minimum. Actually, here is 2 also. But now, this is between G and F. F is a standalone set, I know. G is not alone. It has actually G and H is in one set now. Is the set of F equal the set of G? No, they are not equal. Then I can take it. Also, similarly, the next is with 4, A and B. Now, for example, let's take this one. The set of C has C and I. The set of F has F, G, H from the previous case here. Is it safe to add this 4? Yes, then I will add. Now let's look to this one here, 6. This will not be taken. Why? Because the set of I is the same as the set of G. They are in union. They are the same set now. Therefore, this will not be taken. Will be excluded. Similarly, I and H will not be taken. They will be excluded. And if they are taken, then will be cycle. And the minimum squadratic tree says one of its properties that it does not have a cycle. Therefore, 6 will not be taken, 7 will not be taken. Next, I will take the minimum, maybe this 7. Okay. So this is the 7. This will be taken. Next, I have this 8 here. Okay. Sorry, this 8. I will take it. Now let's think about this one. What is the set of B? B has A, H, G, I, C, F, D in the set. What's the set of C? It's the same set. Then, therefore, this H will not be taken in place. And so on and so forth until just give you 1 minute thinking about the algorithm. If you did not understand, just listen. Otherwise, I will start with the times. Okay. I will just clarify something for you. I'll just go to an earlier state. I mentioned that we start with building a forest. Where is our forest here? So, for example, here is a tree, and here is a tree. They are disconnected. Now, in the next, I have now 3 trees. This is a tree, has just only 2 nodes. This is another tree. This is another tree. Then you approach a way that you connect these sub-trees. Okay, this is the idea of Kruskal algorithm. So, then at the end, the last slide here, we have 1 tree. All nodes are connected with the minimum cost. Now with the prime algorithm, which I think will be the last algorithm in this lecture, the idea is different. You want to start from a node and create the tree as once. Okay, we don't need to create a forest and try to approach how to connect them. The prime algorithm is also a greedy algorithm. This is the algorithm. It is basically more like the Dijkstra's algorithm that we have learned in the beginning. Why? Even the way, even the algorithm itself, I mean, sometimes even confuse you from the first look. Because it will start from a specific node, then it will consider all distance to all nodes is infinity, the same as like Dijkstra's. But then we don't update from the distance of the starting point. We just update the edge. We just look to the edge of that node and just update it. Meaning that, for example, with Dijkstra's here, as mentioned before, I was looking to this infinity and say, okay, from A, 1. Then this is also 2. Now with Dijkstra's, I will say from B I can go to C. Yes, good. Okay, then it's actually 1 plus 1 is 2. Okay, then you update. Why? This is accumulated. This is the 0 plus 1, and this is the 1 plus 1, which is actually plus 0. Okay? This is the Dijkstra's update. But with the prime algorithm, no. We just look to the next edge. For example, A to C, 2. Okay, make it 2. A to B, 1. B to C is 1. This is the cost. What if it is 5? I will not sum up things. I just take the cost of this edge and update this node with the cost of that edge. Okay? We will not take a commutative sum to the starting point. Okay, the algorithm is somehow similar. Consider the key for all nodes infinity. And the predecessor is null. We don't know the predecessor, and we need the predecessor always to know how we can from the starting point to this node. We have a queue it's initially empty, and we have R here. R dot B clearly the starting point. Okay, so the point where you start your algorithm. Okay, now you insert all vertices in the graph to the queue. While the queue is not empty, extract the minimum. What is the minimum now? Is actually R dot key 0. All the other one are initially infinity. You start from there. And for each adjacent vertices, for their vertices, you look to the weight and the edge from how you can go to start from to the next vertices, and if it's this, then you update with the weight of the edge, not the sum of. So just only take the weight of the edge. Here is how the algorithm is work. You start at A, you can go from A to B and also H. Now initially B is infinity, C is infinity, I is infinity, all of them is infinity. Now A to B will be actually 4 because infinity is greater than 4, then you update B, it will be reachable by 4. H will be reachable by 8, then you update it by 8. Next, let's start from, do we have more adjacent to A? No. Then let's go with B now and see if it has adjacent. Yes, we have adjacent. H, we have C, we have I. So H is actually 8, right? Do I will take this 11? No, because from B to H is 11, but I have actually I can be connected with H from somewhere else, from A with A as a cost, not H. Therefore, this will not be taken. Then let's go, we will always think about the minimum. From B, I can go to C with the minimum, okay? Then it's 8. Okay, so then this is the one that will be chosen. And we will update the cost of C instead of infinity. Now it becomes 8, not 12. This is the difference between Dirichlet and the prime algorithm. So you need to be careful here. In Dirichlet, we will say C will become 12 because we will sum up all the distance reached to C from A. Here we just update with the cost, the last cost that connect with the previous node, with its predecessor only. Okay, then C become A. What's next? From C, where I can go? From C, I can go to D, to F, to I. What is the minimum of these? It is actually to I. Then I will go to I with 2. Next, from I can go to H and G with 6 and 7. But I have this cost that I can go from C this still. C is discovered, and still I can go further. Therefore, I will not go with 6 or 7. I will go with this 4, for example. Then therefore, I will go with F. Now, from F, I can go to G with 2, and this is the minimum cost. We have also C can discover D here, but it's not the minimum yet. Then I can go to G. Once I'm in G now, the next is actually to go to I, but I is already discovered, or to H, for example, with 1. Okay, then I actually will choose it with 1. Then 6, I will not go with 6. 7, I will not go with 7 because all of these are already visited and discovered to the minimum cost. Then the next is this 7, the other 7, and so on and so forth until you have the minimum spanning tree, and this is the minimum spanning tree. The question, can I end up with the same minimum spanning tree using Kruskal algorithm or Prime's algorithm? So this is the resulted tree applying to the same graph from primes. Just have it in your memory because I will go back and show the result of Kruskal. This is the primes, this is the int. What is not included is this 11, this 8, this 6, 14, and 10. It's not included. Let's go to Kruskal. This is the last. Okay. It's the same. So, is it always the case? No. Because I said before that we could have different minimum spanning tree for the same graph. Therefore, I could actually have the same tree, yes, but not always the case. Here, for example, I decided to go with this 8, not this 8. But if someone took this edge before this one, then it's a different minimum spanning tree with the same cost, but yeah. Okay, good. Do you have any question? Great. If not, then we'll stop this theory lecture here. Just give some information about what we will have next. Until we just will take one more time, like 10 minutes, and then maybe our PAs will. It's good also to mention because we have a good number of attendance today. It's not really very, very good. We expected like 140 students in this class, but still, comparing with the last lecture, we have good number of students. Information about the next lecture. The next lecture will be the last lecture in this course. So this means that in May we will not have any lecture in this course. We will cover. By the next lecture, we will be just covering all the topics. Next lecture will be like, like maybe less time than what we spent in this lecture, because it will be just only a connection topic to the graph, and then we finish, like half an hour maybe, and then after that I will speak about the final exam. What I did so far regarding the final exam, yesterday prepared a list, PDF file which I will share with you. This PDF file contains instruction and guidelines for the final exam. It's already mentioned in the first lecture how the exam will look like. I gave this information but with more details in this PDF. The PDF will tell you all kind of questions, expected that we have multiple choice, we have open questions, distributed to points, the topics that we may focus on. Okay? Like for example, I will have 4 questions. In the PDF I will mention that 20 question will have 15 points on the graph, for example. Another question will be, for example, on the tree with, I don't know, 10 points, so you know the distribution of weight. I also did more work in the multiple choice. Last year I did multiple choice also exam. Part of the exam was a multiple choice. This year I tried to be fair also with choosing the multiple choices. Last time I was maybe find out at the end after having 25, we will have 25 questions for multiple choice. Last time I discovered that, okay, I was not covering all possible things with the course, with my multiple choice. This time I tried to cover everything. Okay, so I selected the multiple choice. But then I thought yesterday it is good if I can also make a table for you that you know, for example, how multiple choice per topic maybe you expect. I guess this maybe will help you in preparing for the final exam in terms of grading weight. If you want to pass, what are the topics that I should focus on first? If I have more time, then maybe I can go with the others. I hope it may help. Okay, I don't know. What I did more, and it took from me a really long time, I prepared the exam, and I prepared the re-exam, and I prepared a third exam, which is called MOCO exam or a demo exam. It's actually mimic the same level somehow of the final exam. I have multiple choice questions and open questions for you, which I will share on the exam. More information will be provided in the next lecture. Okay, I will release it next lecture, the test exam that we will actually can do it, but this is a self-study exam, so we will not do it inside the lecture. You can just only practice things using that exam. Do you have any question that I can also consider in my next lecture about the exam? If you have something specific, yes?
Can we do mock exam outside of the lecture hours?
The test exam, you mean?
Like the mock exam?
Yes,
Yeah, okay.
you will do it after the lecture. So what I expect that you need first to read. You need to read the course and go through the slides. And then before the exam, 1 night or 2 nights or 3 nights, because I will give you also unlimited attempts and this will not be corrected. It will be anonymous also participation. You can do it at any point of the time, and it will be open from next lecture. I will do it until the morning of the date of the exam. It's accessible, you can just do it at any point. The multiple choice question, I can do it automatically correction because I can choose what is the right answer, and you can compare your answers later on once you finish automatically. But for the open one, you need someone to correct them for you. We will approach today with the TAs, with that they can prepare also maybe the answers for you in a file and just share it somewhere. You try to solve yourself and then compare your answer with the provided answer. Or, I guess maybe the other choice would not be graded or not be corrected by any one of us. But you can actually go online, you can go, AI can help you actually. I mean, the same question, if you go to AI, it will give you the answer. And then you compare your answer with the answer you get from AI. And this is, I think, maybe a good procedure because we so far think in the university how we can actually use AI in teaching. And this is could be a possibility to learn because this is a test exam, it's not time to cheat or I don't know. But you can argue, you can try yourself first and then give the question to AI and then get the answer from there and compare with your answer and then start arguing with the AI, why did you change this, why my solution is not correct. Maybe it will be actually your solution is also correct, but the AI solved a different way, and then you can start a discussion which will enable you to learn the topic even more. I myself sometimes also query AI for a lot of things, especially for preparing this lecture. Sometimes have some confusion, for example, why the algorithm we started like this. Then I start also discussing what if I did it this way. Do you have a counter example that this is not correct, for example? Today, for example, I don't know, last night I was actually doing a discussion about how we can discover a cycle in a given graph. And we explained today that we are looking for a gray edge. If we go from gray to gray, then this is backward. Then I start a discussion with the actually black edge is also can give you a cycle. It was actually a long discussion until I was convinced at the end with really some counter examples to see that this is, yeah, okay, it's not really a cycle. I was thinking it's a cycle, but the logic says no. Okay, so you learn, and once you learn, it's like you explain the topic to your friend. And this is one of the best way of learning, that if you can actually go and teach the same concept to your colleagues, then you will remember better. Okay, that's all what I want to mention, at least until this moment. If you have anything you would like that I speak about it in the next lecture, please let me know or just email me, then I prepare for it. Okay, good. Yeah.
Could you remind us if it is open book or closed book?
It's already mentioned in the beginning of the course. Okay, no aids are allowed, except that you can bring with you a sheet of paper if you want to write, prepare your solution, for example, or you can open the Word, Microsoft Word or Notes to prepare your answer before just write a final one. Sometimes you need actually, I don't know, maybe for example a question, calculate the shortest path between, I don't know, and then you need somewhere something to draw and do something by hand, but this will not be corrected. What you wrote also on the Word file will not be submitted only on this server. So no open book, no slides. More information about this will be in the next lecture. But one thing for people maybe who will not join us, just to keep in mind, the exam does not require from you to memorize anything except you will learn the logic. An example. This is the prime algorithm. Do I want to remember a prime's algorithm? No. No pseudocode. You don't need to remember it. But given this one, and if I ask you, given this graph, apply the prime's algorithm and print the minimum spanning tree. Oh, okay, you don't see it. Sorry. Thank you. Okay, back. I will just say. This is the prime's algorithm. This is the pseudocode. Do I need to remember it? No, you don't need to remember it. But given this graph, and if I ask you, please follow the prime's algorithm way to print the final minimum span tree, you should be able to do that. Without giving the graph, you should remember the mechanism. This is what I want from you to learn, not to memorize. And this is why my exam is not an open book. Okay? Now another question that you could expect, given the following pseudocode, which is the prime's algorithm updated because given this algorithm, I can just do something here. Now update it in a way that allows or enables something more functionality. But I will give you that. I will give you this the pseudocode in the example. I say this is a pseudocode updated to enable new function. Therefore, you don't need to remember any pseudocode with all what we have learned in this lecture. But we need to remember the mechanism. For example, stack, given a stack, how we can store the stack, push it from the stack, from. You need to know how to do this in pen and paper, but the algorithm you don't need to remember. Okay. This is all. My question will be looks like this. We need to remember the mechanism, not the pseudocode. The pseudocode, if there is a question to write a pseudocode, that depends on a pseudocode that you have learned in the lecture. For example, depth per search is one of the pseudocode that we have learned. Breadth per search, we learned about trees, a lot of algorithms. Sorting algorithms, for example, merge, I don't know. The merge sort, for example, we have learned, I don't know, 6, 7 types of sorting algorithms. Each one of them has its own pseudocode. And some of them really goes to 2 or 3 slides sometimes. If there is a question to update that algorithm to do something more, then I will bring it to the table. Okay? Otherwise, you need to know how, given an array, how to sort it using merge sort, for example. You need to remember the mechanism, but not to memorize it. Another thing which could be helpful for you also as well is that in the exam, if there is a programming question, then write even a plain English. I will correct, I will consider. So, see the code is acceptable. You know Java, write in Java. You know C++, write in C++. You know Python, Python. You know English, just write in English. But it should be structured English. Say like, for example, here, sentence number 1, we create a for loop. This for loop should come, right like this. Should come from I equals 0 to I equal 10. Then next, this is the block. You say here we start the block of the for loop. Here we end the for loop because I want to understand the structure. Otherwise, then I will correct. The idea of this whole course that you are introduced to algorithmic thinking. I will not test your ability in specific language. Okay, then people who will fail this course, they have no excuse. Okay, good. I think we stop here. And then maybe take a break.